is this on? Did I put it on?
Yes, it's on.
Okay, so thank you, Avi, for the invitation. Thanks for coming. These are all postdocs or so?
Well, you can ask anyone who likes to.
What's the background of everybody here?
Most of them are emeriti, but
Computer scientists. I know one, right? I know. Okay. So yeah, so it's a small group, so you should feel free to stop me. All of this is joint work with, the topic is quasi-random hypergraphs. All of this is joint work with my postdoc, John Lenz, at the University of Illinois. Okay, so the goal of the talk is to try to explain to you everything in this picture. Okay? None of this should make sense right now, but as we go through, slowly this picture should make sense, and then eventually then it should be clear. This happens to be the, should I make it full screen? Yeah. Happens to be, for the real experts, the poset of 6 uniform hypergraph quasi-random properties. But it's a long story, so let's begin with graphs. So it doesn't, interesting.
Yeah, they can move it, or you can shift it a little to the right.
Yeah, so the story begins in the late 1980s with these fundamental papers of Andrew Thomason and Fan Chung, Ron Graham, and Rick Wilson, where they define a bunch of properties that graphs can share, and they showed that these properties are equivalent. And they proved a theorem which has many properties which are equivalent. I want to focus on some of them. Now, the setup for this theorem in this talk and all the theorems that I'll be stating is as follows. So we're going to talk about a sequence of graphs or hypergraphs, Gn with n vertices, and we're going to fix a number p, which is a constant. And we are going to think of these graphs as having density at least p. So the number of edges in Gn is at least p times n choose 2 plus some function of n which goes to which is little o of n squared. All the theorems will have this setup. Sequence of graphs or hypergraphs, density p, constant. And actually I just need density at least p. Okay, so the basic theorem of Chung-Graham-Wilson, originally proved in a different form by Thomason, is that two of the basic properties of random graphs, which I will call disk, short for discrepancy, and expand in this talk, are equivalent to some other properties. Let me just, because these properties will keep coming up throughout the talk and I need you to know the names, let me draw a picture for each of these properties. So disk just states that for every not too small set of vertices, actually for every set, but there's an error term, the number of edges inside is about the density inside is about the density of the whole thing. Okay? So this is the number of edges of the graph inside U, and that has density p.
What do you expect to find in a random graph?
What you expect to find in a random graph with edge probability p. So that's disk, and expand is a bipartite version of disk. Expand says if you take any two sets of vertices and you look at the edges between them, you expect p times the size of the first set times the size of the second set of edges with an error term. Now, what happens if these two sets intersect? And they can intersect, and it's important that you do at some point. If they intersect, then you count the edges inside them twice. And I'll be a little more precise about this. So E of st in this case is just the number of edges with one point in S and the other point in T, counted twice if they are in the intersection. Okay, so these are basic properties of random graphs that we all know and love, and it's easily seen that these two properties are equivalent, right? If you know disk, then you know expand, right? Because you know, so let's see the proof. You know disk, you have to show, so you give me two sets S and T, I need to show you the number of edges is correct. You know how many edges are here because of this, you know how many are here, you know how many are here, so you know how many are here. Okay. And going back is trivial. If you know expand, how do you show disk? You just apply expand with S equals to T. So it's just trivial. These are, but these which become trivially equivalent are not going to be there's going to be a distinguishing factor for them later, and that's why I stress it now. Okay, so these are basic properties of random graphs. And then the theorem was that, and these are easily shown to be equivalent, that these are also equivalent to this other property, which is another property of random graphs, which is that the correct count, you have the correct count for any fixed graph. So fix a graph f, Peterson graph, any graph you want, and you're counting the number of labeled copies. So this is the number of edge-preserving injections. Actually, they don't have to be, it could be homomorphisms because the density is constant. But you're just looking at copies of f inside G. If it was random, if G was random, then that would be the number, right? You map the vertices, n choices, n minus 1, n minus 2, so that asymptotically n to the number of vertices, and then all the edges have to be present, and then there's an error term. Okay, so that property is going to be called count all. And another thing, yeah, maybe I won't stress that now, but here's the first really surprising part of the theorem and powerful part of the theorem, and that is that all you need to do is count cycles of length 4. So count C4 just says that the number of C4s in this sequence is correct. Correct means what it would be if it was a random graph. And if you know count C4, you know count all. Now, one important consequence of this from a computer science point of view is that, from a computer science point of view, is that you can check how many C4s there are in polynomial time. Indeed, there was a famous paper of, there is a famous paper of Alone, Duke, Lefman, Rödel, Euster from 1990s called the algorithmic version of the regularity lemma, where they give an algorithm to decide if a pair of sets is epsilon regular. Because the definition of epsilon regularity, so just think about what definition of epsilon regularity says. It says for any two sets, the pair is epsilon regular if for all subsets of the first and for all subsets of the second, the density between them is the same. That's exactly expand. Okay, so the density, so to check the regularity condition, you need to check expand, which is an exponential time to check because there are exponentially many sets. And what they do in this paper, algorithmic regularity lemma, is they basically show that expand is equivalent to count C4. It's not quite that, because the way they show it is they show that if you know the number of if the degrees of the vertices is correct, and if the common neighbors of most pairs of vertices is correct, then it's epsilon regular. That's basically the same as counting C4s. Okay, so this is an important fact, and I guess it was proved in this theorem, but it was also proved in that theorem around about the same time.
I'm confused about what the O small o.
Good. That was the thing I didn't. Yeah, I was hoping I didn't have to talk about, but I claimed I do. So what does it mean that this property is equivalent to this property? That's the question, right?
No, I mean even if you talk about the discrepancy property.
Okay.
So what do you mean by small o n squared? That there is some.
There is a function. There's a f of n.
That is independent of u.
Yes.
Oh, okay.
Yes. And so what is it, and more importantly also, what does it mean that this property is equivalent to this property? It means that there's, for some function f, there's a function g, and vice versa. So typically these are stated in epsilon delta notation, but for us it was convenient to talk about sequences. Okay. So count C4, lovely property, very important, algorithmic regularity, and so on and so forth. And not at all obvious that if you know how many C4s there are, you know all these other things. Yes?
I'm just curious whether you tighten your control on disk, say, you may change the error term to little o of n. With that, I mean, how much tighter control would you get on the count C4?
Oh, that's, yeah, I don't know.
This is just for dense graphs. It's, you wouldn't, I mean, there are graphs with, I mean, if this O of n, you will be able to handle sets that are very small.
Right.
I mean, there are graphs without C4s, right, which would have discrepancies, like expanders would have this property. The first two properties work well for graphs of bounded degree. You have the right proportion of edges between any two large sets, and you have no C4 or no short cycles at all.
But what if P was still constant? What if P was still 1/3?
Yeah, I don't see it, but the problem is not so interesting if you change the error term. But I have to think precisely about it. Yeah.
That is based on the
of this? Without. Without. Even this proof of Alon, Duke, Lefman, Rodel, Euster was also without. It's just a proof, right? It proves something about finding a regular partition. It proves that you can find a regular partition in the semi-ready regularity lemma context in polynomial time, but the proof does not use no regularity. Nothing, no, easy, reasonably easy proof. And in fact, I'll even show you one of these proofs at some point. Okay, so that's the first part of this theorem. And then this other part, which is also beautiful, is the entrance of the spectral, the eigenvalues. So it says it's equivalent to having the largest eigenvalue of the adjacency matrix of the graph be Pn plus little o n, and the second largest eigenvalue be small compared to n. Okay, so this is the basically a summary of the important aspects of the Chung-Graham-Wilson theorem for us, and this has many implications, applications, and so on. And the goal of this talk is to write down a theorem like this for k uniform hypergraphs. Now, so instead of talking about a graph, you could talk about, let's say, a 3 uniform hypergraph. Edges have size 3. You can think of writing all these statements for 3 uniform hypergraphs in an obvious way. And the story I'm going to tell you is that it's not so obvious, and you can't make the usual claims you want to. Okay. So the the first issue that comes up is the notion that count all is equivalent to disk in graphs. Now, unfortunately, that immediately is not true for hypergraphs. And this construction, which is a very important construction, actually shows this. This was an observation of Rödel related to some Ramsey problem of Ehrlich and Heiner. But for 3 uniform hypergraphs, so k is 3, and for this talk, whenever I say k, you can think of k equals to 3. Disk and count all are not equivalent. Now, if you learn nothing else from this talk, learn this construction. Okay, this is just a beautiful construction, and it shows the issues involved. So I will construct for you, or Ehrlich and Heiner constructed and Rödel observed, that this construction satisfies disk but fails count all. So disk is this, and it fails count. And the construction is the following. Take a random tournament, probability space, take a random tournament, and now I make a hypergraph. I'll draw a picture. Edges have to have size 3, and if this happens, it's a hyperedge. That's the construction. You have n vertices, and you randomly decide whether it should go in this direction or in this direction. Like a random graph, but not quite a random graph. So probability space of size 2 to the n choose 2. You flip a coin for every pair and you decide. When you do this, you get a hypergraph. Right. Okay. So big tournament, flip these coins, and now I form triples. P is 1/4. That's the first observation. What is the probability that this is a triple? This can be in any direction, but given that it's in this direction, this has to be, and this has to be in that direction to form a triangle. So half times half. So the density is quarter. Now, it's not trivial because you don't have independence, so you can't just use Chernoff bounds or something simple to show that it satisfies disk, but it is relatively straightforward to show that. So not only is the density about quarter, but if you take any set of vertices, the number of triples inside that is also about a quarter. Okay, I won't go through that. But the really interesting part about this is that not only does it fail count all, not only does it fail to have a copy of this hypergraph, which has 4 points and all the triples. K43 is the complete 3 uniform hypergraph on 4 points. It has 0 copies of it. Not only it's supposed to have n to the 4 times quarter to the 4 copies of it. That's n to the 4 p to the number of edges, but it has 0. And here's the beautiful proof. Suppose you had a copy of it. These are the 4 points. All the triples are supposed to be there. So this is a triple. That means that you must have had this. This is ABC, ABCD. BCD is a triple. ABC is a triple, and I already told you this, so that means you must have this. And now you see the problem. The problem is that ABD cannot be a triple because both these things point out. And you cannot even have 3 of these 4 edges. Okay, so this construction, and this is what this whole talk is about, is this hypergraph. It's sort of random, but not too random. And that's sort of the moral of the story here. Okay, so we cannot write a theorem just like this, because disk and count all are not equivalent. So that's the one issue that has to be addressed. And this was actually, so the question is, what is equivalent to counting everything? What is equivalent to C4? And this was a combination of results of Chung and Graham, who wrote the first paper on hypergraph quasi-randomness, and subsequently 12 years later by Hayakawa, Rödl, and Skoken, which says that the following are equivalent for K uniform hypergraphs. So think of K equals to 3. Instead of disk, there's another property called clique, which I call clique disk K minus 1, which I will explain to you on the next slide. It's a more complicated, richer property than disk. That property is equivalent to count all, which is clear, right, what a count all is. For any fixed K uniform hypergraph, the number of copies is correct. And that's equivalent to counting one particular object, like one particular hypergraph analogous to C4, the octahedron. This is the octahedron. So the octahedron is the K uniform hypergraph which has 2K points in K groups of 2 and 2 to the K edges, all the edges that go between the parts. Is it clear what the octahedron is?
Sorry, the edges were not clear to me. What are the edges?
So this is when K equals to 3, there are 8 edges. This one, and this one, and this one.
Okay.
There are 8 of them, right? K is equal to 2, it would be exactly C4. So in that sense, it reduces to the previous theorem. So this is a lovely thing. If you know how many octahedra there are, and the number should be correct, which should be n to the k times p to the 2 to the k plus little o of plus some error term, then you know everything.
It's sort of dual to the cube, right?
Yes.
Is this actually a 3D octahedron for K equals 3, or is?
It's an abstract hypergraph, right? So it has k sets, and it has all these edges.
Right, but just in case 3, you know, I mean, you have the faces of an octahedron.
There are no faces, it's just sets. Let's think about it as an abstract hypergraph for this purpose. You could interpret it in many interesting ways, which I don't know all of them. But.
I guess maybe a question is why is it called the octahedron?
Yeah. Yeah, that would be
The triangles that are face of the 3-dimensional
octahedron, right? That's the reason for the name, yeah. But we should think of it as a hypergraph. Okay. Clique disk. Clique disk is a bit more complicated. What is clique disk L? There's a clique disk L for every L, and the one on the previous slide was clique disk K minus 1. So remember what disk is. Disk is, there's a picture of this. For every U.
The wrong thing is that the base set should be the edges and not the vertices.
That's right. Right. And clique disk is more complicated, and let me show you the example just for, don't read it, it's too many parameters. So K equals to 3, L equals to 2. What is clique disk 2 for 3 uniform hypergraphs? It says for every graph, pick your favorite graph. Here I picked a set, U. Here I'm going to pick a graph. Okay. For every graph, I have to look at something. What I look at is how many triangles do I have? Okay. I look at how many triangles I have, and I ask how many of these are hyperedges. Remember, I have a hypergraph here, and I'm trying to tell you if it satisfies clique disk 2. And it satisfies clique disk 2 if for every graph G, if you look at how many triangles there are in G and how many of those are hyperedges, the number of those that are hyperedges is p times the number of triangles. So here's a more formal definition. For every L, clique disk L is the following property. For every L uniform hypergraph G, that means sets of size L, whose vertex set is the same, if you look at the cliques of G, so these are K element sets, all of whose L element sets are from G, and you look at how many of those are edges, remember the edges of H were K sets, it was K uniform hyper. If it was randomly put, then there would be P proportion of those edges, and that should happen.
Can you state in terms of cohomology so that it's far from the boundary? If you write it this term, so it's not equivalent.
I do not. I have no idea how to. What exactly are you asking?
So if you write so you have hypergraph, so you can write for this hypergraph a special complex.
Yes.
And then you can ask how far is from boundary of the previous copy. So does it?
I don't know that it's this. So you want to write this in terms of that? I don't know how to do that.
So because the previous time we saw hypergraph was when Alex Bosko was here.
Yeah. I don't know that it's the same thing, that it can be written in those terms. Yeah, I would have to think.
It looks very similar.
Yeah, I know, right. So let's do it for L equals to 1.
Okay.
What is it saying for L equals 1? For L equals 1, it's saying for every one uniform hypergraph. What's a one uniform hypergraph? It's a collection of edges of size 1. What should be true? It should be true that for all the cliques, the one uniform clique. What's a one uniform clique? It's a set of size k, all of whose subsets are in that set of size 1. For every one, you should be looking at the one uniform cliques, in other words, the k sets, and ask how many of those are edges. And the number of them that are edges should be p proportion. That's disk. So it's exactly what Avi said. Instead of looking at the underlying structure as being a point set, look at it as being a collection of sets of size L. It's a complicated structure. It's actually it's a complicated thing, and it's an important thing in the study of hypergraph regularity. For those who know the history of how hypergraph regularity began, with a paper of Frankel and Rödl in the early 90s. The key notion to prove strong hypergraph regularity theorems is the notion of regularity has to be more complicated than the graph case, and that notion is very, very similar to this. In fact, this property was suggested by Rödl in the early 90s to Chung and Graham, and the reason it was suggested is he had in his mind hypergraph regularity things, and they showed the first two parts of this theorem as a result. And then 10, 12 years later, the count octahedra came in from the Kohayakawa Rödl scope. Okay, so a complicated property, clique disk L. It says look at the underlying structure as being L sets instead of one element sets. That is the theorem. So that's something. So we saw that clique disk k minus 1 is equivalent to counting everything. It's a very strong property. If you know clique disk k minus 1, then you know all the counts. But how about clique disk 1, which is just disk? Is it equivalent to counting anything? This took a while to figure out. Kohayakawa, Nagel, Rödl, and Schacht, and then Conlon, Hahn, Persson, and Schacht in the last 3 or 4 years showed that indeed it is equivalent to counting something. The theorem they proved is that clique disk 1, or disk, is equivalent to counting the collection of linear hypergraphs. So if I give you a linear hypergraph, I'll tell you what that is in a minute, and if you know the correct count of all linear hypergraphs, then you know disk, and vice versa. And moreover, you don't need to count all. You don't need to know the count of all linear hypergraphs. There's a very specific linear hypergraph, which I'll call C4, which I'll tell you about in a bit. That's all you need to know to get disk. Okay, so we're sort of filling in the picture for hypergraphs, right? We have clique disk k minus 1, which is counting everything. We have clique disk 1, which is counting certain things. Let me explain these two properties to you. So what is a linear hypergraph? A linear hypergraph is just a collection of sets such that every two sets have at most one point in common. Okay? So a graph would be a linear hypergraph automatically.
It's like linear 4 lines, 2 lines intersecting at most one.
That's right. Hence the name linear. Yeah. And so that's this. So you give me what's everybody's favorite linear hypergraph? My favorite linear hypergraph is the Fano plane. Okay? So that means if you tell me disk, you know that the correct number of copies of Fano plane. P to the 7, n to the 7 plus little o n to the 7 Fano planes are there.
It's also clear that this is
It's also clear
K43.
is even K for 3 minus an edge is not a linear hypergraph. But C4 is. So what is C4? C4 is not K222, not the octahedron, because that was also not linear, if you remember. It's this thing. So I'm going to define C4 for a 3 uniform hypergraph. You start with an edge. So this is an edge of size 3. And then what you do is you fix, you can think of it as a 3-partite object. The 3 parts correspond to the 3 points. You fix one of the parts and you reflect around that part. So I fixed the middle part, which I now call blue, and I took 2 copies of everything else. So now I have 2 edges which intersect in the middle. Okay. Now what I do is I do the same operation from one of the other parts. So I did it from the right side this time. So I took, this is what I had before. I had this picture before, and this was blue. And now I did this reflection operation on this side. So I took 2 copies of that. I fixed this, and I just took 2 disjoint copies elsewhere. Now what I'm going to do is I have this thing. I'm going to kind of open it up. So I have these two blue vertices, right? And I have these 2 things sticking out from them. I'm going to open it up. These were the 2 blue vertices. So once again, these blue vertices, this was, yeah, so this is the black part and this is the green part.
What the vertices are the square thing.
Yeah, now I changed the vertices, but all you should think about here is the green goes to the green and the black goes to the black.
But I'm just trying to figure out what are the vertices and what are the edges.
Oh, these are the vertices. 1, 2, 3, 4, 5, 6. There are 4 edges. This edge, this edge, this edge, and this edge. Right now there are 4 edges. And you should think of this as a path of length 2. So let's rather than go to the next step, let me show you how this would look if I was doing it for graphs. So let's do the same thing 1 dimensional lower. I start with an edge. That was the first thing I did. Then I said I'm going to duplicate around this path. So the next thing I get is this. Now in the 3 uniform hypergraph I had to do 2 duplications, but here I just do 1 duplication. The next thing I said is I'm going to straighten it out. That's what I've just done over here. Now how do you get a cycle in a graph in this process? So what is this? This is a path of, this is a 2 path, right? So how do you get a cycle? You take another 2 path and you join it here. And then you take another one and you join it here. You do this a bunch of times, and then at the very end, this vertex and this vertex you identify. That's a cycle. So that's the thing we're going to do here. So now we take this 2 path and we copy, so this was the first 2 path that we had. And we take another one and we identify the ends, just like taking a path and then another path. And you can do this as many times as you want. And at the very end, you identify this stuff and that stuff.
So that's not C4.
It's something.
Yeah, if you do it any number of times, it's not C4.
No, if you do it any number of times, it's C2k, C4k. But if you do it just once, it's C4. Yeah. Okay, so is it clear? It's not an obvious thing to kind of.
Anyway, it's a particular graph.
It's a particular hypergraph, right? And it's linear.
So for general K, how many duplications do you get?
K minus 1. So for general K, you do K minus 1 duplication, then you straighten out, then actually, if you just care about C4, like Avi says, you don't need to do any of this straightening out. Then you just do K duplications, no straightening out. Just do, if I just duplicated it, if I did 1 more duplication around here, what I would get is this.
What's the original picture for K higher? Like just go back to how we did the first step.
So I start with an edge, a set of size K. Yeah, and then I duplicate. So it's kind of like this, right? You start with a set of size K. And step 2 would be you duplicate. And step 3 would be you duplicate around this. So now it's hard to draw, right? But there's going to be 2 of these. And then you duplicate around here, and then you duplicate here, then you do this, and you get C. Okay, that's C4.
You're telling us that we should see Cauchy-Schwarz in this duplication.
Eventually, yes.
Yeah, no, sorry.
Yeah, of course. That's
There is a reason for it.
right.
Duplication process.
Okay, so that was, yeah, so then I can tell you. So that was, I just wanted to explain this theorem. And that's where we sort of entered this topic, and now I can describe our results. So we have three types of results. The first is, you may have noticed that there was no eigenvalue in these hypergraph properties. So we introduced Eig, but more precisely, we actually didn't introduce Eig. Avi and Joel Friedman introduced Eig 15 years ago in a paper they wrote on eigenvalues for hypergraphs. But I guess we generalized it and put it in the properties in the context of this quasi-random properties. And I'll tell you a little more about that. The next thing we did is we generalized these theorems of Hayakawa, Nagel, Rödel, Schacht, and Conlon, Hahn, Persson, Schacht substantially. What was their theorem? Their theorem was about this linear and clique disk 1 and C4. We generalized it substantially, and I'll explain that. And the final thing is we looked at all the other properties on hypergraphs that have been studied in the last 20 years, and we basically figured out the relationship between them. There were lots of questions about if you have this property, do you have this property, and so on and so forth. And the picture that I showed you at the very beginning of the talk is the answer to this question, and I'll come back to that. Okay, so what I want to do next is I want to show you how we generalize these theorems, and that takes a bit. So I'm going to define a new hypergraph quasi-random property, which I'm going to call expand 2 plus 1. So first, let's talk about expand 1 plus 1 plus 1. So I want to draw for k uniform hypergraphs a picture similar to what's on the left. So expand 1 plus 1 plus 1 says k is 3, right? Everything works for k bigger than 3, but k is 3, just for simplicity. So if you take 3 sets R, S, and T, how many edges should you have like this? If it were a random 3 uniform hypergraph, that many. Okay, so the property expand 1 plus 1 plus 1, and now you may see what this 1 plus 1 plus 1 means. It means 1 here, and 1 here, is this property. Here's a new property. Expand 2 plus 1. That would be a graph in a set. Expand 2 plus 1 says for every graph and for every set, so the graph is called R and the set is called S, how many edges should you have with 2 points in R and 1 point? How many triples should you have like this if it were a random hypergraph? It would be the size of R times the size of S times P. And what happens if this set intersects with this graph and stuff? You have some double counting, but there's an obvious way to do this double counting. So, which is that you count ordered things, little r comma little s, where little r is a set, little s is in your set, and little r union little s is a hyperedge. So that's the relevant thing that you count, which corresponded to counting an edge in the intersection twice when you had a graph. Okay, so expand 1 plus 1 plus 1 is equivalent to disk. I mean, this is fairly easy. I showed you the proof for graphs, but you all agree that I could do this for 3 uniform hypergraphs just by inclusion, exclusion. Okay, so that part is simple. But how about this expand 2 plus 1? It's stronger. If you know expand 2 plus 1, you definitely know expand 1 plus 1 plus 1. Let's see the proof. Suppose I know expand 2 plus 1. I have to prove 1 plus 1 plus 1. That means you give me R, S, and T, and I have to convince you that the number of triples is correct. And you see it. I have to make a graph to use expand 2 plus 1. The graph that I make is the bipartite graph between R and S. Okay, good. So 2 plus 1. And not only do you see this proof, but you see why it worked, right? It worked because this partition was a refinement of this partition. Okay, but the converse is false. This is less easy to see. So in other words, there is a sequence of graphs which satisfies 1 plus 1 plus 1 but fails 2 plus 1. And you can generalize this for k, and it's fairly straightforward. For any k, you can take a partition, which I call pi, k1 plus k2 plus kt. Make sure you don't just take the number k by itself, so that's why I call it a proper partition. And you can define expand pi for any partition to be for every collection of k1 sets and k2 sets and k3 sets and kt sets, how many edges do you have which form an edge from the k1, the k2, and so on. And this is expand pi. Okay, so this is the generalization. It's a stronger property because of this. Strictly stronger property.
Probably not so difficult to see that it is stronger if you simply take, I mean, we know that to get 1 plus 1 plus 1 expansion, you can take random walks on expanded graphs.
That's not how we did it. Okay.
So if you have any expander or your graph, your initial, you set up an expander or a random graph if you want. And that's
Yes.
That fix it. It's unrelated to the other graphs.
Yes.
I'm just going to define the hypergraphs. Hypergraphs are going to be just path of length 2.
Basically correct, yeah.
So then,
Yeah.
I mean, obviously you won't have the expand
Right.
2 plus 1 because all your edges are...
Right, and by Chernoff, you still have expand 1 plus 1 plus 1. Yeah, this is basic, yeah. This is one way of doing it, yeah. We did it somewhat differently.
The most strong thing is here is expand the k minus 1 plus 1, right?
No, we're going to get, it's a partially ordered set.
What?
It's a poset.
Partitions are a poset.
Partitions form a poset. This is the picture I showed you at the beginning, which I'm going to show you again and again and again.
It's not that everything is, so if you have expansion of k minus 1 psig 1, then you have all the...
It's not, there's no one element that's on top of everything, yes. It's supposed there are maximal elements. Okay, so this is our theorem. Now I can state our theorem. This is our theorem that is the analog of the very first theorem I started the talk with, the Chung-Graham-Wilson theorem. You give me a k, you give me a partition pi, and you give me a hypergraph sequence with density at least p, k uniform hypergraph. The following are equivalent. I haven't told you anything about this, but there's something called eigpi, which has to do with the eigenvalue with respect to this partition of the hypergraph sequence H. And there's a first eigenvalue, and there's a second eigenvalue. And the first eigenvalue should be Pn to the k halves, and the second eigenvalue should be small compared to this. And if k is 2, you see that this is exactly the Chung-Graham-Wilson condition. The eigenvalue will be Pn, and the second eigenvalue will be little o of Pn, little o of n. But I have to tell you more about this. Expand pi, I have now described to you this property. Count pi linear. This is a class of hypergraphs that is bigger than the class of linear hypergraphs, and count C pi 4, which is a specific hypergraph which is kind of like that C4. And also you could just count cycles of length 4L with respect to this partition pi. Okay, so this is the generalization of that result. Notice that I don't have something that like count all, right? In fact, that example at the beginning shows you can't have such a thing. Okay, so I need to tell you what is pi linear and what is C4. Sorry?
What is eigpi?
And I have to tell you I also.
Pi 4L, is that, are the last two things both pi linear?
Yeah, yes.
So like do number 3 and 4, like does the fifth one
These are not,
follow from?
no, if you, I mean, everything follows because we proved it, but
But I mean, I just mean,
no, it's like C4 and C8 and C6. Go back to the very first theorem. If I told you how many C4s there are,
oh, it just needs to hold for one 4L, not for all L.
that's right.
What is this condition?
Yeah.
For any L.
No, there is, yeah, if you just know one of them.
You just know one L.
Right.
You get all L.
That's right.
Yeah.
That's right. And that L could be L equals 1, or it could be some larger. Okay, this is a,
just want, the fact that count all doesn't follow because of this example you showed with the tournament. That's not true, because in the tournament case you didn't show that it was
right. I don't know that, in fact, it's not, I don't know that it doesn't follow because of the tournament, but it doesn't follow because of something else.
yeah, but the tournament
In fact, I'm pretty sure it,
have the property
yeah.
of,
In fact, I'm sure it doesn't follow from the tournament, because otherwise we would have used the tournament. We used some other construction, right? Yeah. But the tournament kind of explains to you the philosophy of everything. Exactly, randomness, but not too random. Okay. Pi linear is a bit of a pain to describe. Let me, you could read it, but let me just show you what it means for a simple case. What does it mean? 2 plus 1, pi equals 2 plus 1. What does it mean that a 3 uniform hypergraph is 2 plus 1 linear? It means the following. First I'll lie and then I'll fix the truth. It means that for every edge, which has 3 points, there is a partition of the vertices into a set of size 2 and a set of size 1, such that every other edge which intersects this edge respects the partition. So every other edge should do this or this or this, but should not do this. So what would be pi? What would be 1 plus 1 plus 1 linear? It would say for every edge there's a partition into 3 sets of size 1, 1, and 1, such that every other edge intersects this edge inside a partition. That just means linear. So 2 plus 1 linear will say that you can, for every partition into 2 and 1, it respects the partition. Now, no, there is a partition. There is a partition. Now, as it turns out, but for every edge there's a partition also, right?
So you need this.
For every edge there is a partition. Now, actually, you can do a little bit more. You don't need. You can order the edges one by one, and just require that the previous edges in the ordering respect the partition for the current edge, kind of like defining a tree. That's what's written over here. Right, so let me give you an example of a hypergraph. So this is a nice hypergraph. This is 2 plus 1 linear. Do you agree? Actually, yeah. So for every edge, I can partition it into 2 points and 1 point, so that every other edge has 1 point. In fact, this is the C4 2 plus 1, which was the other thing I was going to define for you. So that's what this definition is saying.
By the way, are those two definitions of bilinear equivalent? Like you gave one and then you fixed it by saying it's ordering business?
No, the definition is with the ordering. They're not equivalent. The real definition is with the ordering, but I didn't want to bother you with that. You can get, if you only require it for an ordering, that enlarges the class of objects that you can consider. I can find you a hypergraph which is not in one and is in the other. There has to exist an ordering. That's right. There is an ordering of the edges and there is a partition of each edge, such that blah blah blah. And what is this C pi 4? C pi 4 is rather simple. You start with C4 for T uniform hypergraphs. And you remember I had these k-partite graph which I duplicated to get the C4. So I had these k parts, and now it's not k, it's T. All you do is you blow up each vertex in the first part into k1 vertices, each vertex in the second part into k2, each vertex in the tth part into kt. And so an edge which used to have size t now has size k1 plus k2 plus kt, which is k. So what would be C4 2 plus 1? You start with a t equals to 2 here. You start with a C4 as a graph, and it's bipartite. You have 2 parts. This is one part and this is the other part. And in the first part, you make every vertex into 2. So I make it into 2. And the second part, I make every vertex into 1. So I leave it. So an edge which was a size 2 now becomes an edge of size 3. And this has become 2. That's this thing. You can do this for any partition pi. Okay, so that was that's this theorem. Okay, and the same thing for 4L. Now you have to do those paths, and then you blow up accordingly. So I have now explained to you the bottom half of this picture, right? So on the bottom of this picture, so these are quasi-random properties. I decided to take k equals to 6 because it's big enough that I can show the complexity and small enough that I can draw it. So on the bottom there are these properties: disk, clique disk 1, count linear. This was that theorem of Hayakawa, Nago, Rorschach, or 1 plus 1 plus 1. And now there is this pochette. And you already saw how, you've already seen how any of these implies any of these. The same proof that 2 plus 1 implies 1 plus 1 plus 1. But in fact, there's a clear separation. And more importantly, there's no relationship between these two things if they're not. So this is the refinement, partition. That's the refinement. Okay. What is dev, and that's the last part of the talk. Right, what is dev? You also know what CDs are, by the way, right? Clique disk. Clique disk. This is this business over here, right? So the clique disk 5 is equivalent to counting everything, and then the clique disks do this until you get to clique disk 1. And I hope you also see when k equals to 2 what this whole picture is for graphs. This whole picture is one point, because the bottom of this picture and the top of this picture are the very same thing. Yeah, dev. Dev is a property that was central to the study of hypergraph quasi-randomness by Chung and Graham. It's not a pleasant property, but this is deviation L. So here's what deviation L is for a k-uniform hypergraph. What you do is you look at sets. You look at sets which have k minus L ones. So in here you have 1, 1, and L twos. So you have a 1, a 1, a 1, a 1, and then a 2, a 2, a 2, a 2, a 2. Just abstract vertex sets in the hypergraph. And then you look at how many edges you have that go across this partition. Okay, so the total number of edges that you'd have is 2 to the L. Now, you could have is 2 to the L. That's the total that you could have in the hypergraph. Now, you count how many you have. It could be you have an even number, or it could be you have an odd number. If you have an even number, you remember it and you say plus 1. If you have an odd number, you say minus 1. And then you add up all these plus 1s and minus 1s over all possible ways to choose vertices with this partition. And if it cancels, almost cancels, then it satisfies deviation. That's what I've tried to write. The difference between the number of even and odd squashed octahedra is small compared to the total number of octahedra. There's k plus L vertices totally that you're looking at. So there's n to the k plus L choices. If the cancellation happens, then you satisfy deviation. It's
people that have seen multi-party communication complexity and looked at discrepancy there, this would be the same.
Yeah, and I remember that in their paper also, actually, in one of the early papers. Yeah.
In one of the early papers.
Right.
Of
That's right.
yeah.
It may be this is where they were coming. I don't know which came first.
I'm not sure which came first. The Mubayi and Segedi paper is 1990.
They're all around the same time.
About the same time.
Yeah.
Right.
Right. So this explains these deviations. Maybe what it doesn't explain is the chain that you see, that if you know deviation 6, you know deviation 5, and so on. But it explains what the properties are. And Chung and Graham proved the top. Chung and Graham proved that if you know deviation k, so deviation k would say that L is k. That means you don't have any of these. Deviation k just says look at the number of k 2, 2, 2, 2, 2s and ask how many of them are even, how many of them are odd. If they cancel, then you know clique is k minus 1. Yeah, and what we did is for every pi, for every deviation, for every L, we showed this theorem. And you see, it was not obvious at all to us, right? So deviation 2 is bigger than all of these pi's, but it's not bigger than any of the CDs, not even bigger than CD2. It's unrelated to CD2. On the other hand, the CDs are related in a weird way to the pi's. You see the pattern? What is CD3 above? Is 3. And it's an if and only if state. So this picture on the top was very murky. So Fan and Ron had some implications, and they had some wrong statements which we had to fix, and it took us a while. So each of these each time you don't see a line, that means we had to come up with a construction to have that of a hypergraph sequence which has some property and doesn't have some other property. And unfortunately, the tournament construction didn't work for anything. We needed to do more tricks. But the tournament construction guided us very heavily. CD2 equals dev3 implies CD2.
Oh, okay.
Is,
CD5 is equivalent to dev6.
Yeah.
CD4 is not.
No, not equivalent. So dev6 implies dev5.
dev6 implies dev5, dev5 implies CD4.
And a line with one being above means the above one implies it.
Right.
Not equivalent.
Okay, but what did you say on the previous slide about CD? You say dev? Oh, no.
No.
Dev. Go back.
This.
Dev k implies cd k minus 1.
Yeah.
Right. What I'm supposed to be saying is the top of this picture.
One back one, please.
Yeah, this is supposed to be the top.
Just the top. Okay.
Just the top. So this was Chung and Graham. This was Chung and Graham. Actually, this whole thing was Chung and Graham. And then Rodel and others put K2222 up there. but this was murky, this picture, and this didn't exist. And this existed about 2 years ago, the bottom.
You're going to prove something.
Maybe. I'll show you something. I haven't talked about eigenvalues, so I should tell you about eigenvalues. So, what is eigenvalue? What is lambda 1? What is lambda 2 of a hypergraph? Now, as I said, we base our definitions on definitions that we learned from a paper of Joel Friedman and Avi, and this is what they told us for 3 uniform hypergraphs. Okay, so I'm going to state it in terms of not tensor products because it becomes too complicated to do that. So think about W as being the n-dimensional space over the reals where n is the number of vertices, and define the adjacency map of the hypergraph just like the adjacency matrix of a graph to be a map from W cross W cross W to the reals, which takes a basis, which takes the vector Ex, Ey, Ez to 1 if x, y, z is an edge. So Ex is a long vector with zeros everywhere and a 1 in one position, position x. So this is like the hypergraph.
This is just like how you build an adjacency matrix of a graph.
Exactly. Yeah, and then you extend it to the whole space by linearity. And this is the spectral, we call it the spectral norm, or maybe Avi called it spectral norm, is the supremum of this map over the unit ball. And that's the largest eigenvalue with respect to 1 plus 1 plus 1. And the second largest eigenvalue with respect to 1 plus 1 plus 1 is kind of like what you would do in a graph to get the second largest eigenvalue. You would subtract off the all ones matrix times the degree. And the all ones matrix is the role the thing that plays the role is the all ones map J. So this is the map such that every basis vector gets mapped to 1. That's the J map. And this k factorial E over n is just the density P. So lambda 2 is the spectral norm of that. That kind of kills the first eigenvalue. But we don't know what the third eigenvalue is and the fourth, and we don't know how to do such definitions. And maybe it's interesting to do such things. Yeah, lambda 1 is just this one, and lambda 2 is this one.
There is a recent paper of Benang and Reta, which does
similar things.
Well, extend, no, so
Oh, to many eigenvalues.
Well, yeah, they have a notion of eigenobjects for tensors.
Okay, so for graphs and for deregular graphs, you may have seen that these are exactly the same as the usual eigenvalues. Deregular graphs. And now, how do you do it for general pi? Now I give you a partition, 2 plus 1, and I want to know what the eigenvalue is, largest and the second largest. So what I do is I define a T-linear map tau pi, T-linear pi map tau pi, and all I do is I group the vertices according to the partition. So tau pi will be a map from W tensor W, if I'm doing 2 plus 1, cross W to the reals where maybe I'll tell you. So what would the definition be? What would tau pi of A1 tensor A2 comma A3 be? It would be just tau of A1, A2, A3. It would just be ungrouping. It's really an accounting trick and nothing more. This is just grouping and ungrouping. So that's how you define. So this is what we did because we had these new properties. So we defined these new eigenvalues, and then it's clear what the largest eigenvalue is, right? The spectral norm of tau pi, and the second largest is the spectral norm of this minus j. And with this definition, actually with the definition that Avi and Joel gave, this famous fact that you need in all this quasi-random business, hypergraph expander mixing lemmas, is triviality. It's basically a two-line fact, two-line proof. So the crucial fact that we need is to relate eigenvalue eig to expand. That was one of the crucial things. So if you know eig, you should tell me expand is true. Expand is asking me about how many edges are in here. And it's saying that the number of edges in here should not differ too much by the expectation. And if you know eig, then you can just take the characteristic vector for this set and apply the map to this characteristic vector, and the main term is the number of edges and the error term is the definition of second largest eigenvalue. So indeed you have and these sets don't have to be one element sets, they can be k1 element sets, k2 element sets, as long as things have been defined in the with the right domain, and we do. So that's how you relate eigenvalue to the expand. And the other thing is, how do you relate to C4? And maybe I will just show you just one little proof.
Here S1 is like if you have partition of say K1, K2, so on KL, when S1 is of size K1.
Yes, yes. So the domains have, yeah. It's like this 2 plus 1 that I wrote over there. It was surprisingly easy to do this. I mean, it didn't require anything, just the notation. But in terms of the hypergraphs, it actually gives you something non-trivial. So let me remind you of this proof, which you asked me about at the very beginning. How do you show that if you know something about if you know I, how does that imply that you know C4? So we'll see which way I'm doing it. We'll see what I want to say. So the way you connect these two things is I'm back to graphs, and then I want to just tell you how. I'll end by telling you what we need to do how we prove this theorem. So you take the adjacency matrix of a graph. I'm trying to relate eigen C4, okay? And you take its fourth power, and you take its trace. And you know what this does. This counts the number of C4s. So this is the number of C4s with some error term, but it's not such. It's a matrix to the fourth power.
You're walking from any vertex 4 times.
Matrix.
You are not in the graph.
Yeah, so in fact you're asking the thing I'm going to end with, but it's a graph right now. So this is true on the one hand. On the other hand, it's the sum of the fourth powers of the eigenvalues. Okay? And if you know the first eigenvalue, and that eigenvalue was, if you remember, it was p times n, that already equals to, now Avi is right. If you know the number of C4s, which is going to be Pn to the 4, and the first eigenvalue is Pn, that's already gives you that. But then the second eigenvalue is nothing. Okay? And that's the way you go from C4. So how do we prove this theorem for hypergraphs? We do the same proof. But the problem is it takes 20 pages instead of 2 lines, right? Because you don't have a matrix. You have this map. So you have to multiply matrices here, but you have to multiply these maps. So you've got to figure out what the multiplication should be. Okay, it should be something that does what the matrix does. Then you need to figure out what the trace should be. Then you need to figure out that when you raise a map to a power, the eigenvalue gets raised to the power as well. Okay, and then you need to figure out what is it that this counts, and it counts the thing I told you it counts, the C pi 4. And if you make all that precise, then you get the theorem that we had for the equivalence between these properties. Thank you.